Hey fellow nerds, today we are going to learn clippers. We will start by understanding the need for clipping. Then we'll learn what is a clipping circuit. We will learn series and parallel clippers, negative and positive clippers, and we'll be doing lots of design challenges. Let us start with the need for clipping. Sometimes signals go beyond what a circuit can handle. Too much voltage can damage the components or cause distortion. For example, think about a cell phone that is getting closer to the base station. The strength of the signal increases as it gets nearer, and without control, it could become too strong, causing issues in the communication system. Also, some other times, certain parts of the signal aren't useful for the application. That is where clippers come in. They remove specific parts of a waveform while leaving the rest intact, making the signal safer and more practical to use. Clippers use diodes to change the appearance of the applied waveform. For example, consider this. We have a sinusoidal signal that is going as an input to our electronic circuit. But our circuit has a safe limit. It cannot have its input be greater than that. So, this particular input waveform could damage our circuit. So, to protect our circuit, we could do this. Clip the part of the waveform that is above the safe limit so that our input is clean and safe. A typical clipping circuit looks like this. It has a diode and it has a resistor. Input is applied over here. Where is the output taken from? Well, output can be taken across the diode or the resistor, depending on our requirement. Assume that we take our output across the resistor. The output is then connected to a load. When the load is also included in the circuit, it will look like this. Clearly, the diode is connected in series with the load. So we call this a series clipper. Let us go on and design some series clippers. Our first design challenge is what you have on the left side over here. Our input is a sinusoidal signal. What we want is this. We want the negative half of the waveform to be clipped. Now, this is actually the output of a half wave rectifier. We already know how to do it. We just have to take a circuit that looks like this. The famous half wave rectifier. In the positive half cycle, the diode will get positive here, negative here. It will be forward biased and output will be equal to the input. In the negative half cycle, the diode will get negative potential here, positive potential here. It will be reverse biased. We will model it as an open circuit. No current is going to flow through the resistor. Output will be 0. We will get exactly this. If we draw the input-output characteristics of this circuit, this is how it will look like. When input is positive, V output is equal to the V input. So we get a straight line with a slope equal to 1. When input is negative, output is 0. So we get a horizontal line on the x-axis. Let's see the next challenge. Here again we have a sinusoidal input. The output has the negative half cycle but not the positive half cycle. We have done this also before. All you have to do is take a half wave rectifier, change the direction of the diode. Here the diode will be forward biased for the negative half cycle of the input and it will be reverse biased for the positive half cycle. That will give us this output. If we draw the input-output characteristics, this is what we get. When input is positive, output is 0. So we get a horizontal line on the x-axis. When input is negative, we get output is equal to input. So we get a straight line with slope equal to 1. Well, this was easy. Let us see the next challenge. Let's take the first one. Input is a sinusoidal waveform. Output is the same waveform but it is shifted V units upwards. What we had at 0 is now at V. What we had at V0 is now at V0 plus V. So all we have done is took the same waveform but shifted it V units upwards. It is very easy to do this. All you have to do is add a cell in your circuit like this. Input is applied over here. Output is taken across the resistor. And a cell of potential V is given over here. Let us use KVL to write the output voltage. I'll start from here and go clockwise. V input is from negative to positive. So I'll write down V input. As we go, V is also from negative to positive. So plus V. V output is from positive to negative. So I have to write minus V out is equal to 0. Or we can write V output is V input plus V. So V output will be V input shifted V units upwards. That is exactly what we wanted. If we draw the input output characteristics, this is how it will look like. I have taken input voltage on the x-axis and output voltage on the y-axis. So this equation can be compared with y equals mx plus c. V input corresponds to x, V output corresponds to y. M is the slope, it is the coefficient of x. Here the coefficient of V input is 1, so we have a slope that is 1. C is the y-intercept, here it is V, so we have a y-intercept of V. In the next challenge, we have to do exactly the opposite. Whatever we had at 0 is now at minus V. Whatever we had at V0 is now at V0 minus V. So basically, the signal has shifted V units downwards. That means we want the output to be input minus V. This is also very easy to get done. All we have to do is change the polarity of the cell in the circuit. Let us again use KVL. I'll start from here and go clockwise. V input is from negative to positive. I'll write V input. The cell is from positive to negative. It is in the opposite direction. So I will write minus V. V output is also from positive to negative. So minus V out is equal to 0. Or we can write V output is V input minus V. If we draw the input output characteristics, this is what we get. Let us compare this equation also with the equation of a straight line. Y is equal to mx plus c. V output will be on the y-axis. V input will be on the x-axis. M is the coefficient of x, it is the slope. Here coefficient of V input is 1, so slope is going to be plus 1. The only difference is C or the y-intercept is minus V. If we plot it, this is what we get. Slope of the graph is 1 and the y-intercept is minus V. Our next challenge is to design a circuit that gives us an output that looks like this. First, we have to understand what is happening here. Let me take our input waveform. I'm going to shift it V units downwards. Now I will remove whatever is above the x-axis. Isn't this exactly what we want? So our circuit should do two things. It should shift the waveform V units downwards and remove or clip whatever is above the time axis. The waveform has to be shifted V units downwards, and since the upper part is being clipped, we call it a positive clipper. Let's try to design the circuit. To make our circuit a positive clipper, we will take the half wave rectifier circuit and switch the directions of the diode like this. We also want the waveform to be shifted V units downwards, which means we have to add a cell in the opposite direction of the input, like this. Let's do the analysis and see if this actually works. Here for the diode to be conducting, it needs negative potential on this side and positive potential on this side. The cell is already providing that, but V input is in its opposite direction. So when V input becomes greater than V, the diode will get positive potential here and negative here. It will be reverse biased. In that case, we can model the circuit like this. Since the diode is in reverse bias, it is modeled as an open circuit. Since it is an open circuit, no current is flowing through the resistor, which means potential across it is 0. Output voltage is taken across the resistor, so V output is 0. Now, when V input is less than V, the diode will keep getting negative potential here and positive potential here, which means it will be in forward bias, and we can model the circuit like this. Since the diode is in forward bias, it is modeled as a closed circuit. To get an expression for the output voltage, let us use KVL again. I'll start from this point and go clockwise. V input is going from negative to positive. So let's write down V input. Cell is going from positive to negative, which is in the opposite direction. So minus V. Output is also from positive to negative in the opposite direction. So minus V out is equal to 0. Or we get V output is V input minus V. So output is input minus V, but whenever input is greater than V, the output is 0. That means this much part of the input will be clipped off. Plus it is shifted V units downwards. So we get exactly what we want. Let us draw the input-output characteristics of this circuit. When V input is greater than V, output is 0. I have shown that over here. When V input is less than V, output is V input minus V. Y is equal to mx plus c. M is 1, c is minus V. Slope is 1, y-intercept is minus V. Let us see the next challenge. Our input is again the same and this is the output we want. First, let's figure out what has happened. I'll take our input. I will shift it V units upwards. Now I want to clip whatever is above the time axis. This is exactly the output that we want. So the circuit we are going to design should do two things. It should shift the waveform V units upwards and clip whatever is above the time axis. Let us write it down. The waveform has to be shifted V units upwards, and since we are clipping the upper part, it is a positive clipper. Let us design the circuit. For a positive clipper, again we can take a half wave rectifier and switch the directions of the diode. To move the waveform upwards, we have to add a cell of potential V in the direction of the input voltage. We'll get a circuit that looks like this. Let's do the analysis and see if this actually works. Here V is in the direction of the input voltage, so we have negative here and positive here, which means the diode is already in reverse bias. That means unless the input voltage becomes more negative than minus V, the diode is going to be in reverse bias. In that case, we can model the diode to be an open circuit. Let's draw the circuit model when the V input is greater than minus V and the diode is in reverse bias. Since the input voltage is not negative enough, the diode is in reverse bias and we have modeled it as an open circuit. Since the circuit is open, no current will flow through the resistor. Potential across it is 0. Output voltage is 0. If the input voltage is negative enough, that is, if V input is less than minus V, the diode will be forward biased and we can model it as a closed circuit, like this. Let's use KVL to write an expression for the output voltage. I'll again start from this point and go clockwise. Input is going from negative to positive. So I have V input. Cell is from negative to positive. It is in the same direction of the input, so plus V. Output is from positive to negative. It is in the opposite direction. So minus V out is equal to 0. Or we can write V output as V input plus V. What we can see is whenever V input is greater than minus V, output is 0. Otherwise, output is input plus V. This is exactly what is happening over here. Minus V is over here. Whenever the input is less than minus V, we have something in the output. Everywhere else, the output is 0. When input is minus V, our output is minus V plus V, that is 0. When input is minus V naught, our output is minus V naught plus V. Let's plot the input-output characteristics. It will look like this. Whenever V input is greater than minus V, output is 0. I have shown that over here. Whenever V input is less than minus V, output is V input plus V. Let's use the equation of a straight line. Y equals mx plus c. M is the slope, c is the y-intercept. Here m is 1, c is V. So the graph will look like this. It has a slope 1, but I said y-intercept is v. See, if you extend this line like this, it will intercept on the y-axis at a point over here, and that will be equal to v, our y-intercept. Let us see the next challenge. First, let's figure out what is happening. I'll take my input signal. I will shift it v units downwards. Now, I will remove everything that is below the time axis. This is exactly what we want as our output. So the circuit we are going to design should do two things. It should shift the waveform V units downwards and clip everything that is below the x-axis. Let's write it down. The waveform has to be shifted V units downwards, and since the negative part is being clipped, this is a negative clipper. Let's design the circuit. To clip the negative part, I will take a half wave rectifier. To shift the waveform V units downwards, I will add a cell that is in the opposite direction of the input voltage, something like this. Input goes from negative to positive and my cell is from positive to negative in the opposite direction. Let's also make sure the value is V so that the waveform is shifted exactly V units downwards. Let's do the analysis to see if it actually works. The diode needs positive potential here and negative here to be switched on, but the applied potential V is giving it negative here and positive here. So unless input voltage is more positive than V, the diode is going to be in reverse bias. So when V input is less than V, we can model the circuit like this. Diode is in reverse bias, so I have modeled it as an open circuit. Since it is an open circuit, no current will flow through the resistor, which means potential across the resistor is 0, which means output voltage is 0. Now, when the input voltage becomes positive enough, that is, when it becomes greater than V, the diode will become forward biased and we can model it as a closed circuit like this. Diode is in forward bias, so it is a closed circuit now. Let us use KVL to write a relation between output voltage and input voltage. I'll start from this point and go clockwise. V input goes from negative to positive. We have V input. V is from positive to negative in the opposite direction. So minus V. Output is from positive to negative again in the opposite direction of input voltage. So minus V out. This is equal to 0. Or we can write V output is V input minus V. According to the analysis, whenever the input voltage is less than V, we get V output is 0. And that is exactly what is required over here. V is this much, and whenever the input is less than that, that is at all these places, output is 0. Whenever V input is greater than V, that is over here, this is what we get as output. When V input is V, we get the output as V minus V, that is 0. When V input is V naught, we get the output as V naught minus V. So basically between these 2 points, our output is V input minus V, which is exactly what we have written over here. Let's plot the input output characteristics. Whenever V input is less than V, output is 0. I have marked that over here. Whenever V input is greater than V, we have V output is V input minus V. Y is mx plus c. M or the slope is plus 1. C or the y-intercept is minus V. So I have a straight line whose slope is 1. Its y-intercept is supposed to be minus V. I have not shown that. See, if you extend this line like this, it will intercept the y-axis over here and this point will be minus V. Let us see the next challenge. Input is still the same. Output should look like this. First, we have to figure out what is happening. Let me take my input. I'll shift it V units upwards. Now, I will clip whatever is below the time axis. This is exactly what we want as our output. So my circuit should do two things. Shift the waveform V units upwards and clip the negative part. Let's write it down. Waveform should be shifted V units upwards and it should be a negative clipper. Let's design the circuit. To clip the negative part, I will take a half wave rectifier. To shift the waveform V units upwards, I will add a cell of potential V in the direction of the V input. I'll get a circuit that looks like this. Let's do the analysis and check if it actually works. The cell has its negative terminal here and positive terminal here. It is giving the diode positive potential here and negative here. So the diode is going to be switched on by the cell. That means unless the input voltage becomes negative enough, the diode will be switched on. So V input has to be less than minus V so that the diode will go to reverse bias. Until then, it is going to be in forward bias. Let's draw the circuit model when V input is less than minus V. Here the input voltage is negative enough, so the diode is in reverse bias. That means we can model it as an open circuit. Since it is an open circuit, no current will flow through our resistor, output voltage is 0. When V input is not negative enough, that is when V input is greater than minus V, the circuit model will look like this. Here the diode is in forward bias, so I have modeled it as a closed circuit. Let's use KVL to write a relation between V out and V in. I'll start from this point and go clockwise. V input goes from minus to positive. V input goes from negative to positive. So I have V input. V goes from negative to positive in the same direction. So plus V. V output is from positive to negative. It is the opposite direction. That means minus V out is equal to 0. Or we can write V output is V input plus V. According to the analysis, whenever input voltage is less than minus V, output should be 0. This is exactly what we have over here in the graph. Minus V is over here, and throughout this time V input is less than minus V, and you can see output is 0. Everywhere else output is V input plus V. When input is 0, output is 0 plus V. When input is V0, output is V0 plus V. Let us draw the input-output characteristics. When input is less than minus V, output should be 0. I have plotted that over here. When input is greater than minus V, output should be input plus V. Using y is equal to mx plus c, slope should be 1 and y-intercept should be V. So I get a straight line like this whose slope is 1, y-intercept is V. Let us solve a problem now. Determine the output waveform of the sinusoidal input. Input is sinusoidal, its peak value is 20 volt. I can see the circuit is a half wave rectifier that is modified by using a cell of 5 volt. Since it is a half wave rectifier, or since the diode is in this direction, the negative part will be clipped. So what we have is a negative clipper that is biased by a 5 volt cell. I can also see that the cell is in the direction of the input voltage. Input voltage is from negative to positive. Cell is also from negative to positive. So it is going to shift our waveform 5 volt upwards. In short, the waveform will be shifted 5 volt upwards and the negative part will be clipped. To plot the output, let us first take our input. Let's get another version of it that is shifted 5 units upwards. So the peak point will come to 25 volt. Since we have a negative clipper, let us clip the negative part of the output. This is what our output is going to look like. Can you figure out what this point is? You can see that when the input becomes lesser than that value, output is 0. That means when the input is lesser than that value, the diode should become reverse biased, no current should flow through the circuit, and output should become 0. In the circuit, we can see the 5 volt has positive potential here, negative potential here. It is already giving positive here and negative here to the diode, so it is keeping the diode in forward bias. That means unless the input voltage is negative enough, the diode is going to be in forward bias. So input voltage should be less than minus 5 so that the diode will go to reverse bias. which means this point should be minus 5 volt. Also, what is this point? This part of the output is actually this part of the input shifted 5 unit upwards. So whatever we had at 0 will now be at 5 volt. You can also find out these values by properly analyzing the circuit, which I actually recommend. Just pause the video and try to do the analysis. Till now, we have taken the output of the clipper across the resistor. How about we take it across the diode like this? Output is taken across the diode, so the load will be connected over here. Once the load is connected, the diode will be in parallel with the load. Since diode is parallel to the load, we call this a parallel clipper. Let us now do some design challenges based on parallel clippers. This is the first one. My input is a sinusoidal wave. My output is this. I want the positive half cycle intact and the negative half cycle should be clipped. We know this is the output of a half wave rectifier, but the difference is we have to take the output across the diode instead of the resistor. So let us try that. Just like a half wave rectifier circuit, my circuit has a resistor and a diode. Only difference is output is taken across the diode. Here, if input is positive, the diode gets positive potential here, negative potential here. It will be in reverse bias and we can model it as an open circuit. The circuit model will look like this. Since the circuit is open over here, whatever is given at the input will be seen at the output. So V output is equal to V input. Also, when input is negative, the diode gets negative potential here and positive potential here. It will be forward biased and we can model it as a closed circuit. The circuit model will look like this. The output is shorted, which means output is equal to 0. And this is exactly what we wanted as our output. Since the output is taken across the diode, this is a parallel clipper. And since the negative part is being clipped, this is a negative clipper. We can call it a parallel negative clipper. If we draw the input output characteristics, this is how it will look like. When input is positive, we have a straight line whose slope is 1 because V output is equal to V input. When input is negative, output is 0, so we have a horizontal line on the x-axis. Let us see the next challenge. Again, I have the same sinusoidal waveform as the input. At the output, I want to clip the positive half cycle and keep the negative half cycle. This is pretty simple. All we have to do is change the directions of the diode. This will be our circuit. When input is positive, diode gets positive potential here and negative potential here. Diode is forward biased. That means we can model it as a closed circuit. The circuit model will look like this. Obviously, the output is shorted, which means output is equal to 0. When input is negative, diode gets negative potential here and positive potential here. It will be reverse biased. We can model it as an open circuit like this. Obviously, since the circuit is open here, whatever is given at the input is exactly seen at the output. So V output is equal to V input. Since output is taken across the diode, this is a parallel clipper. And since the positive part is being clipped, this is a positive clipper. We can call it a parallel positive clipper. If we draw the input output characteristics, this is how it will look like. When input is positive, output is 0, so we have a horizontal line on the x-axis. When input is negative, output is equal to input, so we have a straight line whose slope is 1. Let us see the next challenge. Again, I have the same sinusoidal input. At the output, I want the clipping to happen at V. Everything above V is being clipped, so we can consider this to be a positive clipper. In the previous case, the clipping happened at 0 level. Now the clipping is happening at V. That is the only difference. So we need a positive clipper and the clipping should happen at V. To do that, first let's take a normal positive clipper circuit. Here, if input becomes positive, the diode will get positive potential here and negative potential here. It will be forward biased and we can model it as a closed circuit. That will make the output shorted and output will become 0, or we can say the waveform is clipped. But in this particular case, we want the clipping to happen only when input is V. That means the diode should not be forward biased unless input is V. I can do it by simply adding a cell over here whose potential is V, like this. The cell is already giving a positive potential here and negative potential here for the diode. So unless the input voltage is in the opposite direction to that and it is greater than V, the diode will not go to forward bias. Or the diode will be in forward bias only when V input is greater than V. In that case, we can model the circuit like this. When V input is greater than V, the diode is forward biased, so we have replaced it with a closed circuit. Now you can see the output is taken exactly across a cell whose potential is V. So V output is going to be V. Also, when V input is less than V, the diode is going to be in reverse bias. We can model it as an open circuit like this. Since the circuit is open over here, whatever is given at the input is exactly seen at the output. V output will be equal to V input. And this is exactly what we wanted as our output. Whenever input is greater than V, output should simply be V. Otherwise, output should be equal to input. Let's draw the input-output characteristics. When input is greater than V, output is equal to V. You can see that over here, when input is greater than V, output is equal to V. When input is less than V, output is equal to input. You can see that over here, when input is less than V, we have a straight line whose slope is 1, which means output is equal to input. Let's go to the next challenge. Again, we have the same sinusoidal input. In the output, the clipping has happened at minus V. Again, the upper part is being clipped, so we can take a positive clipper, but the clipping should happen at minus V. Let us start by taking a positive clipper circuit. Earlier, when we added a cell with positive terminal here and negative terminal here, the clipping happened at V. If we want the clipping to happen at minus V, all we have to do is switch the direction of the cell. Negative terminal here and positive terminal here. Let us do that. Let's do our analysis to see if it actually works. The cell is already giving negative potential here and positive potential here for the diode. It is already in forward bias. So we can say only when V input is lesser than minus V will the diode become reverse biased. Until then, the diode is going to be forward biased. When V input is less than minus V, then only the diode will get a more negative potential over here than what it already has over here. Only then it will become reverse biased. So when V input is less than minus V, we can model the circuit like this. Diode is in reverse bias, so I have modeled it as an open circuit. That means whatever is applied at the input is exactly seen at the output. V output is equal to V input. When V input is greater than minus V, the diode has a lesser negative potential here than what it already has here. That means it will be forward biased. We can model it as a closed circuit. The circuit model will look like this. Now the output is taken directly across a cell of potential V, but the negative terminal is connected to the positive of the output. Positive terminal is connected to negative of the output. So output is going to be minus V. And this is exactly what we wanted as our output. Whenever input is greater than minus V, output should simply be minus V. Also, when input is less than minus V, output should be equal to input. Let us plot the input-output characteristics. When input is greater than minus V, output should simply be equal to minus V. You can see that on the graph. When input is greater than minus V, output is simply equal to minus V. Also, when input is less than minus V, output should be equal to input. That also you can see on the graph. When input is less than minus V, we have a straight line whose slope is 1, which means output is equal to input. Let's see the next challenge. Again, we have the same sinusoidal input. At the output, the clipping has to be happened at minus V. An important thing is the part below minus V is being clipped. So this is a negative clipper. So we need a negative clipper and clipping should be happening at minus V. Let us start by taking a negative clipper circuit. Here, if the input is negative, the diode will get negative potential here and positive potential here. It will be forward biased and our output will be shorted, which means output is 0, which means the negative part is clipped. But we don't want the entire negative part to be clipped. We only want the part that is less than minus V to be clipped. Just like in the previous case, if the clipping has to happen at minus V, we have to add a cell of potential V with negative terminal here and positive terminal here. Let us do that. Let's do the analysis to see if this actually works. The cell is giving a negative potential here and positive potential here to the diode, which means it is in reverse bias. It is an open circuit. For the diode to be in forward bias, it needs a more negative potential here than what it already has here. That means the input voltage should be less than minus V so that the diode can be forward biased. So when V input is less than minus V, we can model the circuit like this. The diode is forward biased, so I have replaced it with a closed circuit. Output is directly taken across a cell of potential V. But negative terminal is connected to the positive of the output, positive terminal is connected to the negative. So output is going to be minus V. Now if the input is greater than minus V, the diode will get a lesser negative potential here than what it already has here. So it will be in reverse biased. We can model it as an open circuit like this. Since the circuit is open here, whatever is applied at the input will be exactly seen across the output. Output will be equal to input. And this is exactly what we wanted as our output. Whenever input is greater than minus V, output should be equal to that. Whenever input is less than minus V, output should simply be minus V. Let us plot the input-output characteristics. When V input is less than minus V, output should simply equal to minus V. You can see that over here. When input is less than minus V, output is here, which is minus V. Also, when input is greater than minus V, output should be equal to input. You can see that also here. When input is greater than minus V, we have a straight line whose slope is 1, which means input is equal to output. Let us see the next challenge. Input is still the same sinusoidal signal. Clipping is happening at V. The negative part is being clipped, so we need a negative clipper. We need a negative clipper that clips at positive V. Let us start by taking a negative clipper circuit. For the clipping to happen at positive V, we have to add a cell of potential V with its positive terminal here and negative terminal here. Let us do that. Let's do the analysis to check if it actually works. The cell is already providing positive potential here and negative potential here for the diode, so it is already switched on. It will only be switched off if it gets a higher positive potential here than what it already has here, which means only when V input is greater than V, the diode will be switched off. So when V input is greater than V, we can model the circuit like this. The diode is switched off or in reverse bias, so I have modeled it as an open circuit, which means whatever is applied at the input will be exactly seen at the output. V output is equal to V input. Now, when V input is less than V, the diode has a lesser positive potential here than what it already has here, which means it will be in forward bias. We can model the circuit like this. Diode is in forward bias, so it is a closed circuit. Output is directly taken across a cell of potential V. Also, positive terminal is connected to positive of the output, negative terminal is at the negative of the output. So V output is equal to plus V. And this is exactly what we wanted as our output. Whenever the input is greater than V, output should be equal to input. Whenever the input is less than V, output should simply be V. Let us plot the input output characteristics. When V input is greater than V, output should be equal to input. So, when input is greater than V, we have a straight line whose slope is 1. When input is less than V, output should simply be equal to V. That you can see over here. When input is less than V, output is simply V. Now, let us see the best challenge in this video. Input is still the same sinusoidal signal. At the output, I want clipping to happen at V1 and at minus V2. Everything above V1 should be clipped. Everything below minus V2 should also be clipped. How do we do this? We know how to do them separately. We know how to clip everything above V1. We also know how to clip everything below minus V2. To clip whatever is above V1, we need a circuit like this. This is a positive clipper and the clipping will happen at V1. To clip everything that is below minus V2, we can use a circuit like this. This is a negative clipper and the clipping will happen at minus V2. If we want both of these to happen, we have to combine the two circuits, which is pretty easy actually. Check out this branch. Its upper end should be connected to the resistor over here. Its lower end is connected to the negative of the input. Same way, in the second circuit also, if you check out this branch, this point is connected to the resistor, this point is connected to the negative of the input. So we can just put them together like this. Now, let us do the analysis to check if this actually works. Let us start by assuming the magnitude of V1 is greater than the magnitude of V2. Now, let's make the circuit model when input is greater than V1. Let us start with this diode. The cell is already giving it a positive potential here and a negative potential here. It is reverse biased. It will only be forward biased if the input is more positive here than what it already has here. That means when V input is greater than V1, this diode will become forward biased. We can model it as a closed circuit. The second diode already has negative potential here and positive potential here from the cell, which means it is reverse biased. When V input is greater than V1, it is getting more positive potential here, which will only keep it reverse biased, so we can model it as an open circuit. Since the circuit is open here, no current will flow through this branch. We can just remove it. The output is taken directly across this cell of potential V1. Positive terminal at positive of the output, negative terminal at negative of the output. So V output is going to be equal to V1. And this is exactly what we wanted. When input is greater than V1, output should simply be equal to V1. Let us try to model the circuit when V input is between V1 and minus V2. The first one is over here. It has a positive potential here and negative potential here. It is already reverse biased. It will be forward biased only if the input becomes greater than V1. But here V1 is greater than Vin or Vin is less than V1. That means this diode will stay reverse biased. We can model it as an open circuit. For the next diode, it is getting a negative potential here and positive potential here from the cell. It is in reverse bias. It will be forward biased only if it gets a more negative potential over here. That means only when V input is less than minus V2, the second diode will become forward biased. But here the condition is V input is greater than minus V2. So this diode is also going to stay reverse biased. Let us replace it by an open circuit. Since the circuit is open over here and over here, no current is going to flow through both of these branches, which means we can just remove them. Now, whatever is given in the input is exactly seen at the output. V output is equal to V input. You can see over here that this is exactly what we wanted. Whenever input is between V1 and minus V2, output is equal to input. Let us now model the circuit when V input is less than minus V2. Let us see the first diode. It has positive potential here and negative potential here from the cell that makes it reverse biased. It will be forward biased only when the input has a more positive value than V1. That is when V input is greater than V1. Here V input is less than minus V2, which is not enough. That means the diode is going to stay reverse biased. We can replace it by an open circuit. For the second diode, it has negative potential here and positive potential here from the cell that makes it reverse biased. It will be forward biased only when it gets a more negative potential here than what it already has here. That means V input should be less than minus V2 so that this diode can be forward biased. And here the condition is V input is less than minus V2. So this diode will be forward biased. We can replace it by a closed circuit. Since the circuit is open over here and no current will flow through this branch, let us just remove it for now. You can see the output is taken directly across the cell of potential V2. But negative terminal is at the positive of the output. Positive terminal is at the negative of the output. So V output is going to be negative of V2. And this is exactly what we wanted. Whenever the input is less than minus V2, the output should simply be minus V2. Let us now plot the input-output characteristics. When input is greater than V1, output should be equal to V1. You can see that over here, when input is greater than V1, output is simply equal to V1. When input is between V1 and minus V2, we have a straight line whose slope is 1. That means V output is equal to V input. When input is less than minus V2, output should be equal to minus V2. You can see that over here, when input is less than minus V2, output is this, which is equal to minus V2. Let us now solve a problem. Determine the output waveform for the given input when the diode is ideal. This is a simple positive clipper. We have already analyzed it. The only difference we have is input is not sinusoidal, it is a square wave. But whatever the input is, a positive clipper is going to clip the positive part of the waveform. So the output will look like this. Positive half cycle is clipped and negative half cycle is still here. Let us solve another problem. Determine the output waveform for the given input. Diode is ideal. Here the input is a triangular waveform, but that doesn't matter to us. Let us check the circuit. From the direction of the diode, we can see this is a negative clipper. From the direction of the cell, we can see the clipping is going to happen at plus 4 volt. So everything that is below plus 4 volt will be clipped. The output will look like this. Whenever the input is less than 4 volt, output is simply 4 volt. Whenever the input is greater than 4 volt, output is equal to input. Let us see the next problem. Determine the output waveform for the given input. The diode is a silicon diode. Its knee voltage is 0.7 volt. We have the same input from the previous question, same circuit. Only difference is diode is not ideal. Let us do proper analysis to find the output. The diode is getting positive potential here and negative potential here from the cell already, and it is of 4 volt. We have a silicon diode with knee voltage 0.7 volt. So as long as it has a potential of 0.7 volt across it, it will be in forward bias. That means as long as the potential that it gets over here is less than 3.3 volts, it will be forward biased. Let us draw the circuit model when input voltage is less than 3.3 volt. Diode is in forward bias, so I have replaced it with a cell of potential equal to its knee voltage, which is 0.7 volt. The negative terminal of the cell is where the N side of the diode is. Positive terminal is where the P side is. Output is taken across the two cells. The cells are in the opposite direction. We have plus 4 and minus 0.7. So output voltage is going to be 4 minus 0.7, that is 3.3 volt. Again, when input is greater than 3.3 volt, the diode will get a higher potential here and a lower potential here, which means it will be reverse biased. So we can model the circuit like this. Since the diode is reverse biased, I have modeled it as an open circuit. Since the circuit is open, no current is going to flow through this branch. So whatever is given at the input will be exactly seen at the output. V output is equal to V input. Now, if we plot the output waveform, this is what we get. Whenever input is less than 3.3 volt, output is supposed to be 3.3 volt. You can see that over here. Whenever input is less than 3.3, output is simply 3.3 volt. Also, whenever input is greater than 3.3 volt, output should be equal to input, and that is exactly what we have over here. Let us solve a final problem. A signal must be limited at plus or minus 100 millivolt. Assuming the knee voltage is 700 millivolt, design the circuit. So the signal must be limited at plus 100 and minus 100 millivolt, which means we have a double parallel clipper. Let's take a circuit that will do positive clipping and negative clipping. This diode will do the positive clipping, this one will do the negative clipping. Now, the positive clipping should happen at plus 100 millivolt. That means this diode should be switched on when the input is plus 100 millivolt. For the diode to switch on, it should have at least 700 millivolt across it. It already has plus 100 on the P side, so it should have minus 600 on the N side so it can switch on. So what we want over here is minus 600 millivolt. That can be provided by adding a cell of potential 600 millivolt with its negative terminal here and positive terminal here. Let us do that. Now, the negative clipping should happen at minus 100 millivolt. That is, this diode should be switched on when the potential here becomes minus 100 millivolt. The diode has minus 100 millivolt on the N side. It needs at least 700 millivolt across it so that it will be switched on. That means on the P side, we should be providing plus 600 millivolt. That can be done by adding a cell of potential 600 millivolt with its positive terminal here and negative terminal here. Let us do proper analysis to check if this actually works. Assume that we get a potential over here that is greater than 100 millivolt. The first diode already has minus 600 millivolt on its N side. Now, if it gets anything that is more than 100 millivolt on the P side, this is going to get a potential that is greater than 700 millivolt across it. It will become forward biased. On the other hand, this diode has positive 600 millivolt on its P side. If it gets a potential that is greater than positive 100 millivolt on the N side, the difference between the potential across N side and P side will become less than 700 millivolt, which means the second diode will be reverse biased. So when the input is greater than 100 millivolt, we can model the circuit like this. First diode is in forward bias, so I have replaced it with a cell with potential equal to its knee voltage 700 millivolt. The other diode is in reverse bias, so I have replaced it with an open circuit. Since the circuit is open here, no current will flow through this branch. So let us remove it from the circuit. Now the output is taken directly across these two cells. We have positive 700 millivolt and negative 600 millivolt. So output voltage is going to be 700 minus 600, that is 100 millivolt. Now let us see what happens if we get a potential over here that is less than minus 100 millivolt. For the first diode, it already has a negative 600 millivolt on its N side. If it gets a potential on its P side that is less than minus 100 millivolt, the difference between the potentials across N and P side is going to be less than 700 millivolt. That will make it reverse biased. For the other diode, it already has positive 600 millivolt on its P side. If it gets any potential that is less than minus 100 millivolt on the N side, the difference between the potential at P side and N side is going to be greater than 700 millivolt, so it will be forward bias. In that case, the circuit model will look like this. Since the first diode is reverse biased, I have replaced it with an open circuit. Since the second diode is in forward bias, I have replaced it with a cell with potential equal to its knee voltage. I have also made sure that the negative terminal of the cell is where the N side of the diode is, and the positive terminal is where the P side of the diode is. Again, since no current is going to flow through this branch, let us remove it from the circuit model. Now, the output is taken across these two cells. We have a plus 600 millivolt and minus 700 millivolt. So output is going to be 600 minus 700 minus 100 millivolt. Now let's see what happens when the input is between 100 millivolt and minus 100 millivolt. Let us see the first diode. It already has a minus 600 millivolt on its N side. It will be forward biased only if it gets a potential over here that is at least equal to 100 millivolt. So for this diode to be switched on, input should be greater than 100 millivolt. But here the condition is 100 millivolt is greater than V input or V input is less than 100 millivolt. So this diode will not be turned on, it will be kept in reverse bias. Let us see the second diode. It has plus 600 millivolt on the P side from the cell. For it to be in forward bias, it needs at least minus 100 millivolt over here. So as long as V input is even negative than minus 100 millivolt, this is going to be in forward bias. But over here, V input is greater than minus 100 millivolt. So this diode is also going to be kept in reverse bias. So we can model the circuit like this. Both diodes are in reverse bias, so they are modeled as open circuits. No current will flow through both of these branches, so let us remove them from the model. Now, whatever is applied the input will be seen at the output. V output is equal to V input. This is what we can conclude from the analysis. Whenever the input is between 100 millivolt and minus 100 millivolt, output is equal to input. But whenever input is greater than 100 millivolt, it is clipped. Whenever input is less than minus 100 millivolt, also it is clipped. Which means the circuit works. So that's all about it for today. See you in the next video. And don't forget to subscribe.